If you sit down right now and ask a chatbot to draft an email for you, or you use an AI tool to generate some photorealistic image of a cat riding a skateboard on Mars.
Right, as you do.
As you do, exactly. When you do that, you are interacting directly with the ghost of a single document from 2017.
Yeah, it really is the foundation of everything.
It is. We see these massive society-altering technological shifts, and, well, it usually feels like they must be the result of a million disconnected breakthroughs happening all at once.
Oh, totally. Like a huge rep of different inventions.
Right. But when you look under the hood of almost every single piece of modern AI, you find that practically all of it traces back to one paper published by a team of Google researchers.
Yep, the famous one. Attention is all you need.
Attention is all you need.
Right.
Which is exactly why today's deep dive is entirely dedicated to that specific shift.
It's rare in computer science to see a single architecture rewrite the rules of an entire field so quickly. I mean, we're talking about a complete paradigm shift here in how machines process information.
Exactly. So our mission today is to demystify this transformer neural network architecture. We've gathered a whole stack of sources for this.
Yeah, the original technical papers, J. Alamar's visual guides, Hugging Face documentation, plus a lot of historical context.
We really want to explain how this technology actually reads, how it writes, and the mechanics of why it completely revolutionized artificial intelligence. So consider this your shortcut to finally understanding all those buzzwords you keep seeing in the news.
And look, I know the math under the hood involves complex matrices and, high-dimensional vectors, but the core concepts are beautifully intuitive.
They really are.
Once we strip away the jargon, the underlying logic of how a transformer thinks actually makes a lot of sense.
So to appreciate the solution, I think we have to understand the problem first. Let's go back to 2017, before the transformer existed. How was AI handling language back then?
Well, the standard for dealing with any sequence of data, whether that was a string of text or a voice recording or time series data, was recurrent neural network.
Right, RNN.
Exactly, RNNs. And specifically, researchers relied heavily on a variant called long short-term memory networks, or LSTMs.
Okay, so what was the bottleneck holding those back?
The fundamental characteristic of those models was their sequential nature. They processed text exactly how humans read it. So word by word, strictly from left to right.
Which, I mean, that seems like the most logical way to build a reading machine, right? Human language is sequential, so the machine should be too.
You'd think so, yeah. It mimics human reading, but it creates a massive short-term memory problem for a machine.
How so?
Imagine the model is processing a really long paragraph. It reads the first word, compresses that information into a hidden state, and then passes it to the second word.
Oh.
Then it combines the second word with the first, passes it to the third, and so on. Every single step of the way, the information from the very beginning of the sentence gets diluted.
Ah, I see.
Yeah, so by the time an RNN reaches the final word of a long paragraph, the signal from the first sentence has degraded so much that the model has, well, largely forgotten the initial context.
I always think of RNNs like trying to read a dense, complex novel through tiny moving people.
Oh, that's a good analogy.
Right. You can only see one word at a time.
Mm-hmm.
And you try your hardest to hold the entire plot in your head as you scan across the page. But eventually, the cognitive load is just too high.
Exactly. You lose track of who the characters are or what the original premise even was.
The information just gets lost in the chain.
It does. And the 2017 paper looked at that sequential chain and just decided to throw it out entirely.
Just tossed it.
Yep. They abandoned recurrence. They abandoned the peephole. The transformer was designed to look at the entire sequence of words simultaneously.
And looking at the entire page all at once doesn't just help with context, right? It fundamentally changes the hardware equation.
That was the absolute secret weapon of the paper. When you process a sequence one word at a time, you are stuck in a computational traffic jam.
Right, because step 2 cannot happen until step 1 is finished.
Exactly. But if you process everything at once, you can utilize modern GPUs, those graphics processing units.
Which are built for that exact thing.
Yeah, these chips are explicitly designed to do thousands of matrix multiplications in parallel. By breaking that sequential chain, the researchers unlocked massive parallelization.
And the results were insane, right?
Unbelievable. The original transformer model achieved a record-breaking 41.8 BLEU score.
Which is the standard metric for evaluating translation accuracy, right?
Right, on an English to French translation task. And the crazy part, it trained in just 3.5 days using only 8 GPUs.
Wow. which was a fraction of the time, and the compute cost that the older RNN models required to achieve, frankly, worse results.
Yep.
But okay, let's unpack this because this brings up a massive logical problem.
Yeah.
If the transformer sees the entire page all at once, in parallel, how does it know which words are actually connected to each other?
That's the million-dollar question.
Let's use the classic example from our sources. The sentence is, the animal didn't cross the street because it was too tired. How does a machine, looking at that whole sentence at once, know that the word it refers to the animal and not the street?
The solution to that exact problem is the absolute heart of the 2017 paper. It's a mechanism called self-attention.
Okay, self-attention.
Yeah. Self-attention allows the model to dynamically bake the understanding of other relevant words into the specific word it is currently processing.
So it's building context on the fly.
Exactly. When the model processes the word it, the self-attention mechanism runs a calculation that links it strongly to the word animal and much less strongly to the word street.
I really want to break down how it actually calculates that linkage, because honestly, it sounds like magic until you look at the vectors.
It does sound like magic, yeah.
According to the source material, every word is first turned into an embedding, which is a 512-dimensional vector. So
Yeah.
basically a giant list of numbers representing that word's core meaning.
Right, a coordinate in space.
But the model doesn't just use that embedding, does it? It creates 3 new vectors for every single word.
It does. It creates the query, the key, and the value vectors.
Query, key, and value.
Yeah. The model takes the original word embedding and multiplies it by weight matrices that the system learns during its training phase. And this creates 3 smaller 64-dimensional vectors for each word.
The YouTube analogy from the AI hacker source is, I think, the best way to visualize this.
Oh, I love that analogy. Go for it.
So imagine you pull up YouTube and you want to search for a video. The text you type into the search bar, that is the query.
Right. And then the search engine has to figure out what you want. So it compares your query against the keys in its database.
And the keys are, what, the metadata?
Exactly. The keys are the video titles, the descriptions, the tags, all that metadata attached to the content.
And once the algorithm finds the keys that best match your query, it presents you with the value. And the value is the actual video file you're going to watch.
That maps so cleanly to the math of self-attention. So, to find out how much focus the word it should put on the word animal, the model takes the query vector of the word it and calculates the dot product with the key vector of the word animal.
Okay, and a dot product is essentially just a mathematical way of measuring how aligned or similar 2 vectors are in space, right?
Yes, exactly. The higher the dot product, the more aligned the query and the key are. But there's a mathematical catch here.
Oh.
When you multiply large dimensional vectors, the resulting numbers can become massive.
Ah, right.
And if the numbers get too big, it breaks the math later in the process and the model just fails to train.
So how do they fix that?
They scale the score down by dividing it by 8, which is simply the square root of the dimension of the key vectors.
Okay, so just keeping the math stable.
Exactly. And finally, that scaled score is passed through a softmax function.
And softmax just turns a list of numbers into a probability distribution. So everything gets squashed between 0 and 1, and the whole list adds up to 100%.
You got it. The higher the softmax score, the more relevant the word. So the model takes this softmax score and multiplies it by the value vector of the word animal.
So it's keeping the important stuff.
Right. This keeps the values of the highly relevant words intact, but it drowns out the irrelevant words by multiplying them by tiny fractions, like, 0.001.
Okay, that makes sense.
Then the model sums all these weighted value vectors together, and the output is a brand new, context-rich representation of the word it that now literally contains the essence of the word animal.
But wait a second. Language is messy, right? One word can have multiple different relationships at the exact same time.
Oh, for sure.
Like if I say the word bank, it could mean a river bank or a financial institution.
Yeah.
On top of that, a word relates to the subject of the sentence, but it also relates to the verb, the action taking place.
Yeah, there's a lot going on.
If we are just summing everything up into one single vector, doesn't it just turn into a confused, muddy mess of average meanings?
That is a great point, and the researchers anticipated that exact limitation. Their solution was something called multi-headed attention.
Multi-headed attention.
Yeah. They realized that running this query key value calculation just once wasn't enough. So in the original architecture, they ran it 8 times in parallel, using 8 separate independent heads.
So it's essentially analyzing the sentence from 8 different perspectives at the exact same time.
Precisely. It creates multiple representation subspaces. Because each head initializes with different random weights and learns independently, they naturally specialize over time.
Oh, wow. So what does that look like in practice?
Well, one attention head might focus strictly on grammatical structure, like making sure pronouns align with nouns.
Okay.
Another head might focus entirely on action verbs. Another might look for emotional tone or negative phrasing. Each head produces its own output vector.
And then what? How do they combine them?
At the end of the process, all 8 vectors are concatenated, so just stitched side by side, and pass through a final linear layer to compress it back down.
So the model can hold the grammatical structure, the emotional tone, and the context all distinctly in its mind without them blurring together.
Exactly, it's brilliant.
It is. But man, this leads to a massive new problem.
Oh, yeah.
We've abandoned the people. We process everything in parallel. We know exactly how words relate to each other. But by processing all the words simultaneously, we have completely destroyed the sequence.
We threw away the order of the words.
Right. The order of the words has just disappeared. To a system processing everything in parallel, the sentence, man bites dog and dog bites man, contain the exact same words and would look mathematically identical.
And without a sense of order, language is just a bag of words. It means nothing.
So how do we fix this?
To restore that order, the authors had to inject positional information directly into the word embeddings themselves before any of the attention mechanisms even fire.
Okay.
They did this using positional encoding.
Right, and when I was reviewing the source material on this, the mechanics of it threw me for a loop at first.
It's definitely a bit weird.
Yeah, to give the model a sense of order, the engineers used this intricate mathematical trick involving sine and cosine functions of different frequencies.
Yep, the waves.
Right. For odd time steps in the sequence, the model applies a cosine function. For even time steps, it applies a sine function. Why go through the trouble of weaving sine and cosine waves into the data? Why not just number the words 1, 2, 3?
I know numbering them seems so much simpler, but think about the scale of the numbers. If you just number the words sequentially, you run into huge generalization issues.
Generalization issues.
Yeah. Say you train a model mostly on sentences that are 20 words long. The network learns to handle weights associated with the numbers 1 through 20.
Okay, that makes sense.
But if you suddenly feed that trained model a document that is 5,000 words long, the position number 5,000 is a massive alien value that the network has never seen before.
Oh, I see.
It completely warps the math and throws all the learned weights out of alignment.
Ah, so absolute numbering basically punishes the model when it tries to read longer texts.
Exactly. Sine and cosine waves solve this elegantly because they naturally oscillate. They just fluctuate continuously between -1 and 1. They never blow up into massive numbers.
That's super clever.
It is. And more importantly, sine and cosine possess linear properties that allow the attention mechanism to easily calculate the relative distances between words, no matter where they are in the sequence.
Wow.
So the model doesn't just know that a word is at position 400. It mathematically feels the exact distance between position 400 and position 415.
And the field has continued to evolve this concept, right? Our sources highlight alternative positional encodings that modern models use today.
Oh yeah, it didn't stop there.
There's ROPE, which is rotary positional embedding. Instead of adding a wave to the numbers, ROPE uses complex numbers and angles to actually rotate the vector in multidimensional space based on its position.
Yeah, the visual for that is great.
It is. Imagine the word's meaning as a point on a clock face. Its position in the sentence just turns the dial a few degrees.
Exactly. It preserves the core meaning of the vector while embedding its absolute position. And then there's alibi, which takes a completely different approach.
Right, alibi.
Alibi doesn't change the word embeddings at all. Instead, it applies a linear penalty directly to the attention scores based on how far apart the words are.
I thought of it like a proximity tax.
Oh, a proximity tax is a great way to put it.
Yeah, if 2 words are right next to each other, the attention score is untouched. But if they're 100 words apart, the score gets penalized.
Exactly. And the beauty of alibi is that it allows you to train a model efficiently on very short text snippets, but then you can deploy it to read massive, incredibly long documents, and it still perfectly understands the spatial relationship between the words.
Okay, so let's summarize where we are. We have our input text, we've embedded the words, we've injected their positions so the model knows the order, and our encoder has used multi-headed attention to create a deeply contextualized, hyperlinked representation of the entire sequence.
Yep, the machine fully understands the prompt.
But how does it talk back? Let's pop open what Jay Almore calls that Optimus Prime goodness, the decoder.
The decoder is where the actual output is born. The encoder sees everything at once, like we talked about, but the decoder has a totally different job. It operates autoregressively.
Autoregressively, meaning what exactly?
It means it generates text one single token at a time. It predicts the first word, and then it feeds that predicted word back into itself as the input for the second step, looping over and over again.
Wait a minute. If the decoder is using the exact same self-attention mechanisms that look at the whole sequence, couldn't it accidentally look ahead at the answer?
What do you mean?
Well, if it's trying to predict word number 5, couldn't the math accidentally pull information from word number 6?
Oh, it absolutely could, and that would completely ruin the training process. The model has to be forced to predict the future, not memorize it.
So how do they stop it from cheating?
To prevent this, the decoder uses a technique called causal masking, which is often referred to as a look-ahead mask. Basically, the attention mechanism generates a matrix of scores showing how every word relates to every other word. The system takes that matrix and physically masks out all the future words, the ones it hasn't generated yet,
How does it mask them?
by overwriting their scores with negative infinity.
Negative infinity.
Yeah.
That seems a bit extreme just to hide a word.
It is extreme, but it's mathematically necessary. Remember the softmax function.
Right, the thing that turns scores into probabilities between 0 and 1.
Exactly. When you pass negative infinity through softmax, the negative infinity is mathematically forced into a hard 0.
Oh, I get it.
Yeah, this ensures the model puts exactly 0% of its focus on future tokens. It physically cannot cheat. It can only attend to the words it has already generated, plus the rich context that the encoder provided.
And this autoregressive generation, step by step, is exactly how models like the OpenAI GPT series function.
Yes, exactly.
The AI Hacker Source features a really great example of this in action. They primed GPT-2 with a short prompt, and the model autonomously generated a dark sci-fi novel about aliens manipulating a country's elite to keep an iron grip on the populace.
Oh, I remember that example.
Because it generates word by word while attending back to its own previous context, the story actually maintains a coherent narrative thread. Like, it remembers the alien premise 50 pages later.
Which is amazing, and the development of GPT really highlights how the Transformer family splintered and specialized over time.
Right, because the original 2017 architecture featured both an encoder and a decoder working together.
Exactly. But researchers quickly realized you could decouple them depending on what you needed the AI to do.
Like with BERT.
Right, Google created BERT, which is an encoder-only model. It doesn't generate text. It is optimized entirely for deep understanding, classifying text, and search queries.
And GPT is the opposite.
Yep. The GPT models are decoder-only, making them phenomenal at generation. And then models like T5 kept both the encoder and decoder, which is the ideal setup for tasks like translating languages or summarizing long documents.
Okay, so what does this all mean? I want to focus on that generation piece for a second. When the decoder is generating the next word, it outputs a probability list for the entire dictionary.
Right.
Does it just pick a single highest probability word every single time?
It can, yeah. And that approach is called greedy decoding. It just grabs the most likely next word, step after step.
Sounds fast.
It is computationally very fast, but it can lead to repetitive, rigid, or frankly suboptimal sentences. If you only look one step ahead and pick the most obvious word, you might paint yourself into a grammatical corner by the end of the sentence.
So it lacks the foresight to see how a sentence flows.
Exactly. So instead of greedy decoding, many systems utilize beam search.
Beam search.
Yeah. In beam search, the model doesn't just pick the top word. It keeps multiple partial hypotheses active in its memory simultaneously.
Like parallel universes of the sentence.
Basically, it might hold on to the top 3 unfinished sentence branches, exploring a few words deep into each one. It calculates the cumulative probability of the entire branch, not just the single next word.
Oh, wow.
This allows the model to select an overall sequence that leads to a much more natural, coherent sentence with fewer errors.
But expanding all those branches takes compute.
A lot of compute.
And this brings us to a massive mathematical wall that transformers hit as you feed them more text. The sources refer to it as the quadratic bottleneck, or big O of n squared.
Yeah, the quadratic bottleneck is the fundamental limitation of self-attention.
Why is it such a problem?
Well, because the mechanism compares every single word to every other word in the sequence, the computational cost skyrockets as the text gets longer.
Right.
If you have a sentence of 10 words, that's 100 calculations. But if you double the input to 20 words, the compute doesn't double to 200, it quadruples to 400.
Yikes. So it just scales exponentially out of control.
Exactly. If you try to feed a normal transformer a 100,000-word book, the memory and processing power required to compare every single word to every other word becomes just astronomical.
So how are we using AI models today that can digest entire novels or massive code bases in a matter of seconds?
The industry has developed incredibly clever workarounds for this. One major breakthrough was the concept of sparse transformers.
Sparse transformers.
Right, where researchers factorize the attention matrix. Instead of forcing the model to compare a word to everything, they restrict it to looking at a localized subset of words, or they use a strided pattern.
Okay, that makes sense.
Another fascinating solution is the reformer model, which introduced locality-sensitive hashing, or LSH.
Locality-sensitive hashing. How does that actually bypass the bottleneck?
Instead of calculating the dot product between a word and the entire dictionary of the document, LSH runs a sorting algorithm first. It groups similar words into hash buckets.
Hash buckets.
Yeah, so if the model is analyzing the word bank, the hashing algorithm quickly identifies the buckets related to rivers or money. The model then only runs the intense attention calculations against the words inside those specific buckets.
Ignoring the rest of the document entirely.
Exactly. It drops the complexity from growing quadratically down to a much more manageable linear growth, which is O of n log n.
And it isn't just software algorithms either, right? There are massive hardware optimizations at play, like KV caching and flash attention.
Oh, absolutely.
My understanding from the sources is that the actual math isn't always the bottleneck. Sometimes it's just moving the data around.
Memory bandwidth is a massive constraint.
Right. A GPU is like a massive factory, but if the conveyor belts moving the memory into the processors are slow, the whole factory stalls.
That's a perfect way to describe it.
So flash attention minimizes how many times the GPU has to read and write to its main memory, keeping the data closer to the processing cores.
Exactly. But here's where it gets really interesting. Another fascinating speed-up technique that combines software and hardware efficiency is speculative decoding.
Oh, I love speculative decoding. The best way to visualize it is like a corporate office dynamic.
Oh, right, the intern analogy.
Yes. Imagine you have a small, incredibly fast, but slightly less accurate AI model. That's your eager intern. The intern quickly drafts an entire paragraph of text.
Right.
Then, the massive, highly accurate AI model, which is the senior executive, reviews that entire drafted paragraph all at once.
In parallel.
In parallel. If the paragraph looks perfect, the executive approves it instantly. But if the intern used the wrong word in the middle of a sentence, the executive deletes everything after that mistake, corrects the word, and takes over writing from there.
And the reason that office dynamic translates to massive speed gains goes right back to the Transformer's core architecture.
Right.
Because the executive model can process sequences in parallel, it can verify a string of drafted words exponentially faster than it could generate those words one by one on its own. Speculative decoding exploits the fact that checking someone else's work in parallel is simply cheaper than doing it yourself from scratch.
The attention mechanism is just so versatile. We've solved text. We gave it context with multi-headed attention. We gave it order with positional encodings like row B and alibi, and we overcame the quadratic bottleneck.
You did!
But modern AI isn't just text. We have multimodal systems now.
Yeah.
We are talking to AIs that can see, hear, and analyze the physical world. How did this text-based architecture conquer other mediums?
The profound realization in the AI community was that the Transformer's attention mechanism doesn't actually care about text.
It doesn't.
Not at all. It doesn't know what English or French is. It only knows what a sequence of tokens is.
Okay, so what is a token in this context?
A token is just a mathematical representation of a piece of data. If you can figure out how to translate a different medium into a sequence of tokens, the Transformer can master it.
Vision transformers are a perfect example of this.
Yes, absolutely.
Instead of a CNN trying to process an image pixel by pixel, a vision transformer takes an image and physically chops it up into a grid of tiny squares or patches.
Right.
It flattens those visual patches out into a sequence and feeds them into the architecture exactly as if they were words in a sentence.
It's brilliant. And the exact same logic applies to audio. OpenAI's Whisper model takes an audio recording of human speech and converts it into a spectrogram.
Which is basically a picture of sound,
Yeah,
right?
exactly. It's a visual mathematical representation of sound frequencies changing over time. The model chops that visual spectrogram into patches, treats them as tokens, and feeds them into the transformer.
Wow.
The attention mechanism just learns which sound frequencies naturally follow others.
But the example from the sources that truly cemented this for me involves chess.
Oh, this one is wild.
It is. Researchers took a standard text-based transformer and trained it to evaluate chessboard positions. They didn't program it to think ahead or use minimax search trees to calculate millions of future moves like traditional chess engines do.
Right, no look-ahead search at all.
None. They just converted the pieces and their locations into a sequence of tokens. And this model achieved a Grandmaster-level ELO of 2895.
That's just staggering.
It really is. It didn't calculate the future. It simply used its attention mechanism to deeply understand the grammar and the relationships of a winning chessboard.
What's fascinating here is it proves that the transformer is fundamentally a universal pattern engine.
A universal pattern engine.
Yeah. Once a modality is tokenized, whether it's pixels, sound waves, chess moves, or lines of software code, the self-attention mechanism can uncover the underlying rules governing that sequence.
It is the ultimate game of connect the dots. So we started this deep dive exploring the limitations of reading word by word through a peephole with RNNs.
We came a long way.
We really did. We've unpacked how self-attention blasted that peephole wide open, calculating the relationships between thousands of tokens simultaneously using queries, keys, and values.
Yeah.
We saw how sine waves and rotating vectors keep the sequence in order, how causal masking stops the system from cheating, and how clever hashing and hardware tricks keep the whole thing running at lightning speed.
Yeah.
So the next time you ask a chatbot a question or have an AI generate an image, you know exactly what's happening. It's an incredibly fast, highly parallelized mathematical engine looking for the perfect next piece of the sequence.
And, the success of this architecture across so many domains raises a really profound question to leave you with today.
Oh, what's that?
We've seen that if you can tokenize something into a sequence, the transformer can find the pattern. It has conquered language, vision, audio, and strategic games.
Right.
So what happens when we figure out how to effectively tokenize human biology and DNA, or global weather systems, or the massive chaotic fluctuations of global financial markets?
Right.
Is the entire universe ultimately just a complex sequence of data simply waiting for the right attention mechanism to decode it?